Hello everyone, I'm glad to introduce my colleague Alexander Tregubov and me, Arseniy Marinin. We're non-functional test analysts at Exactpro. First of all, thanks for attending the meetup. It's nice to see so many people here, and special thanks to those of you who still keep your attention. Well, let's start. The topic we want to discuss today is mostly related to non-functional testing. Sorry. Oh, sorry? Once more? Oh, okay. I'll try. So the topic we want to discuss today is mostly related to non-functional testing. We want our products to be the fastest and the best in the market, but what does this actually mean? When could we say, okay, it's fast enough, or no, it's too bad? Before answering these questions, we need to gather and interpret some data. Yep. As we know, testing is a process of researching software with an intent of finding software bugs. We'll get lots of different outcomes during this process, but at first we need to process quite big amounts of data to get some visible results. Logs analysis, outcome comparisons, all these activities considering digging into data. In case of non-functional testing, it's getting even worse. We have to go through massive logs in order to produce a single graph. Taking into consideration quite big amounts of data we've produced, we probably expect this graph extremely useful and illustrative. Well, it really depends. Depends on detailization level, specific metric we're monitoring, or the way we've gathered the data. During our presentation, we'll concentrate mostly on latency testing. So what's latency? In general, it's the time when something starts until it ends, like when you send a request until you get the response, or when you put something into microwave until it explodes. It's quite simple here, but in fact, we want to know exact metric we are monitoring and exact way how to do it before gathering some data and perform some analysis. Imagine a situation when you spend the whole week gathering data, performing some calculations. As a result, you produce beautiful graphs and everything is great, latency is low, so it's perfect time to go live. And then, boom, everything is crashed. The client have to wait an eternity to get a response for a single request, so kind of disaster. Maybe it's something wrong with your graph saying everything is good, or it's just completely useless. So let's try to answer a few questions first. What do we really want to measure, and how do we want to measure it? Answers to both questions are mostly related to end-user experience. So we want to simulate user behavior to gather stats which are relevant to a real user. Small example here. Let's imagine we want to gather some latency metrics in the request-response-based system. We could simply use the time between sending client's requests and timestamp taken from application logs on server side. We could even produce everything as great graph, and it will be good looking, but in fact all the requests could just stuck somewhere between the server and the client, for example because of misconfiguration of the middleware. And we'll not see it on our graph because we used the wrong data to produce it. So it's essential to choose the right data to measure. In this particular example, we could use, for example, timestamps from network captures, and it will solve our problem. Take a look at this graph. There is a dependency of drawings and ice cream sales. What do you think about it? Could it be useful? Well, no ideas. So maybe if we want to know the dependency between these two parameters, but if it's essential to an end user to know, for example, ice cream sales dependency on the time of the day, so we'll probably have to ask, have we got the right data to produce this graph? So a few more things until we go forward. Here's another example. It's not a secret that the way how we're measuring the data also affects test results. As we've already seen with the timestamp example, we could simply collect useless stats, so just waste time and money. There is one more thing to deal with. Let's say we get an environment, it's a black box for us, but we know what we want to measure. So we performed all tests, gathered all the statistics, and it's good looking again. However, we connected our test tool somewhere at point B, when the real client is connected somewhere at point A. And as you can see here, there is a firewall. Yeah, this is a firewall in between the client and the server now, and it will definitely affect test results. So we just gathered another useless statistic. Okay, now we know how important it is. Since we do care about end user, we want to simulate user behavior to perform our tests. From the one hand, we could use specification as a tool in order to get an insight on how users behave. Or, what even better, we could use some statistics from similar systems in order to get an insight on this. In some cases, this is possible, but let's say we got only specification. Based on this information, we could think about load composition, like what types of requests usually sent by user, or how often. All this information required to perform the right test to collect the right data. So let's go back to latency. It's not about a single request processing time. It's about behavior in general. In real life, users send lots of different requests of different types, even per second. So to simulate that, we could use different load profiles or configurations. Let's say we could use ramp-up loads in order to identify some system breakpoints, or constant load profile in order to verify if system could handle it during significant periods of time. Whatever profile we'll use will end up with raw data, so quite big amounts of data, to be honest. We'll get lots of timings and logs to process, but basically we want to match some inputs with an output. We should manipulate our data we've gathered and perform some calculations. Only after this we could talk about some latency measurements and stats. Looks like the visualization of all this is the next step, but at first we probably want our data readable. So here comes the first milestone, aggregation. Let's take a look at this chart. What does this chart really mean? How all these points are generated? In fact, there are lots of hits hidden behind each point in this graph. It's just a summary statistic, an average. So what do we lose during such aggregation? Well, let's see. You've probably seen this guy. It's a clear-edge hedgehog. Let's take a look at this beautiful picture. We could go into details and discuss the colors or its friendly and happy face, or we just could take a look at summary statistic like that. So here's an average color of this picture from previous slides. What could we say about a hedgehog based on this? So probably nothing. It would definitely be helpful to get more details here. So here comes the second milestone, distribution. If we want to know more than a hex code, the next step is to look not only at high-level aggregated data. So let's go into a bit more details here. In order to do that, we could use histograms as a tool. So what is histogram? To make one, just take your data and divide it into bins. We could use different parameters to divide our data into groups and get different distributions, like distribution in space, distribution in time, or distribution by request type, whatever. In case if our data are human, we could probably divide the groups by height. So we'll get one separate bin for the ones who are under 1.60 m, one more bin for the ones who are under 1.70 m, and so on. Once we're all done, we just count how many people are in each bin, and here we get a histogram. Well, it's just another chart. But imagine if you know nothing about human race at all, so you have never seen a human in real life. You then might be interested a bit more in the shape of this diagram. Why is it asymmetric, or why there are few tall people and the lack of correspondingly short people in the left? So you'll probably guess the answer. It's mostly due to the fact there are actually two histograms in this picture matched up, one for men and one for women. So if you take a closer look at the right one, you will see that there are at least two types of humans, and the height is distributed differently in these groups. So you now know a bit more about human being. So why don't we use the same approach with this guy, time series chart? So let's take a look at a bit more detailed example. Alexander will help us with that.
So what actually I can say about this graph? So let's say we did the test performance, perform a calculation aggregation by seconds and create time series graph. Actually, during this transformation, a huge amount of our data just dropped out. Looking at this chart, I can only say that average latency is about 720 microseconds. But what if you look at the distribution graph? We can see that there are two groups of messages. The first one has average latency 720, and the second one has average latency at about 1 millisecond. The first group has count of samples much more than 3 times than the second group. At the right side, you can see these two groups separated. It's much informative. We now understand that there are some transactions in the system with a low rate which consume more resources. So we perform tests at 2 releases and we need to compare them. If you look at the time series graph, we can only say that we observed latency degradation with about 20 microseconds. But if we look at the distributed graph, we can actually say that the second group acts kindly different. It curve shift to the right side. So it's a good point to investigate this degradation by looking at the log or resource consumption. Also, we need to understand, is there any additional functionality or amendment was performed in drop 2 in relation to the second group of messages?
So thank you, Alexander. We could dig even deeper to get more details based on this. But at first, let's talk about Jon Snow. You probably know this guy. Oh, sorry, the wrong Jon Snow. This one. Okay. So he's considered one of the fathers of modern epidemiology, mostly because of his work in tracing down the cholera outbreak in London in 1854. His theory faced lots of criticism, but he managed to go through all the statistics and facts to find the truth. So let's take a closer look. Let's start with the fact there were no germ theory in 1854. The main idea was that all diseases are caused by bad air. It was called miasma theory. So Jon Snow had to provide some serious proofs in order to defend his idea, and he did. Jon Snow started with an aggregated statistics and found an interesting fact. Here is a map of London where you can see some colored areas. Each colored region shows the area solved by a given waterwork. The main argument was that people living north of the city got the water piped in from distant sources. But if you live south of the city, your water was from Thames directly, so you can imagine how clear it was. So once Jon Snow gone through the records of cholera epidemic in 1844-49, he found out that a chance of dying from cholera if you live north of the city was 26 per 10,000. But if you live south, it was up to 80 per 10,000. So apparently cholera has something to do with the water supplies. However, this fact met criticism as well. because of miasma theory at first. It was not enough. Hence, he got into details. During cholera outbreak, he managed to localize the disease and narrow down the area to a single water pump at Fortisbroad Street. You can see it in the map. Every single hash mark on this map is the death, so he just put it there based on the statistics which he gathers from birth and death reports. Let's take a look at the detailed map because I'm not sure it's... Here it is. As you can see here, the white dots are death and the red ones are water pipes. Looking at the distribution of data in space, it definitely looks like all the deaths are concentrated around one single pump at Fortisbroad Street. Well, another evidence to prove that cholera was in the water, but not in the air. However, it was still not enough. We can see some separate dots, for example, at the bottom. In order to explain this anomaly, Snow had to work with extremely raw data, like if he had to go into logs or TCP captures or network captures. So, in fact, he had to interview each survived family member. And what did he find? So, in each case, he was able to establish a connection to a Broad Street pump. For example, the cluster in the lower right. In this particular case, there were children who went to school right near Broad Street pump. John Snow found an explanation of each anomaly, and this kind of evidence completely destroyed miasma theory. If the cholera was in the air, how could it choose which building to infect? So, Snow finally convinced others to shut down the pump at Fortisbroad Street, and it stopped cholera outbreak at this point. It was a milestone and let the germ theory happen. Just because John Snow looks not only at high-level aggregated data or statistics, but have a look on the distribution of data behind the statistic. So the message here, it always makes sense to look at the data more deeply. You will be rewarded. For example, you will make your system more stable, prevent unexpected crashes, or even save lives. So, Alexander, it's your turn.
So let's go back to the 21st century. This is distributed of an alert event on March 29, 2011. At the first glance, we could say that most of sites distributed in this graph loaded in interval between 0 and 10 seconds. However, if we take closer, we can observe that right side of this graph spreads more than left. And obviously, there is a bunch of sites loading much slower than others. As John Snow, we could try to look deeper and try to understand what's going on with this slowest one. So, as we can see, this site is completely broken. There are about 169 requests. Images are downloaded from 47 different domains. When the page first starts loading, it takes the CPU for 4 seconds. As the worst things, rendering doesn't even begin for 20 seconds. You're just looking at the black screen. But if we're talking about the faces one, it should be really good optimized, and what you can see here, what is the page intended to say? It is not for arrow. Again, the main idea here is that if we investigate extremes and deviations, we will probably find some useful information that can be used for future improvement of your system. So let's go to our histograms. There are few more parameters which could be useful in data analysis, like percentile. The main idea is here that we took our data and separated to two groups and drop out the worst one. In this example, we take only 99% of samples with better results. It helps us to choose values that aren't related to some random drops of data. Usually, for such kind of data, for data set, we can calculate few more parameters like average, max, and produce separate graphs. Another one, percentile, is a 50 percentile that has special name, it's median. Median also can be used with average results. It was dependent on outages and can be used as main metric. In this example, median is equal to 267 milliseconds. So here is max 99 percentile time series chart. We just drop 1% of the worst results and aggregate data by the seconds. If we observe something like this, I can say that something definitely occurs at the 4th minute of the test. It is a good point to investigate the cause, look at logs and resource consumption statistics. So, to sum up, if we perform latency test, we need to be sure that we're doing it in a correct manner. All tests should be performed in line with real user behavior. After all calculations, we need to be confident that everything taken into account when we're analyzing data. We should use not only high-level aggregated data statistics, but more detailed data. Once you're able to explain all deviations and anomalies in your data, it will definitely help you to make your system works as you expected. That's all. Thanks for your attention.
Yes, hello, thank you for your presentation. You mentioned that it's really important to look at your data and to collect the right data for measuring latency. What happens if accidentally you collect not all the required data or incorrectly collect some partially? What do you do in such situations?
Basically, we do care about that amount of data we could calculate and could use in order to produce some results. So we don't have to gather all the data across a system. So we just looking at the relevant one. So in this case, it's not a problem.
Yes, and maybe a related question to it about dark data, whether if you see something unfamiliar, some dark data in the system, is it worth collecting it at some point during test execution?
Again, so we don't have to gather every single metric in the system. So we predefine something we want to measure and provide some stats for this, and we get only relevant statistics. So we don't have to gather everything.
Okay, thank you very much.
Thank you.
Any other questions? Okay then. Thank you. Thank you very much.
Thank you.